Good day, everyone. My name is Rebecca Lilly with the International Association for Energy Economics. It gives me great pleasure to welcome you to today's webinar entitled, Could Nordhaus Be Right? We are grateful to our speaker, Dr. William Hogan from Harvard University, for today's timely discussion. First, a little bit about the International Association for Energy Economics. We are the largest association specializing in the field of energy economics and provide a forum for the exchange of ideas, experience, and issues among professionals interested in the field. The organization produces 2 professional journals, a newsletter, and holds conferences and virtual presentations, along with a host of other products and services that you can find at our website at www.iaee.org. If you're not already a member of the association, we welcome you to join. A few housekeeping matters in regard to today's webinar before I hand things over to our speaker. First, this webinar is being recorded for those that cannot participate in today's live event. If you have questions for the speaker, please click the Q&A button at the bottom of the Zoom window and type your question. We have allocated sufficient time at the end of this webinar to address your questions. And now I would like to introduce our speaker, Dr. William Hogan, who is the Raymond Plank Research Professor of Global Energy Policy at the John F. Kennedy School of Government at Harvard University. Over to you.
Thank you very much. It's a great pleasure to be here, and let me get my screen. I'm hoping now you can see my screen. Can you see it?
Looks great.
Okay, so it's a pleasure to be here, and I'm going to get right into it. I emphasize that I don't speak on behalf of anybody else. These are just my own views, but focused on climate policy and the green agenda. And sort of background and motivation for this discussion is the challenges of climate change, which is a wicked problem, as we all know, and the scale is global, it covers many generations, the uncertainties can seem overwhelming. I've extracted a few quotes to motivate the conversation here. First from Bill Nordhaus, global warming is a major threat. And then from President Biden, we have it as an existential threat to human existence. A slightly different view comes from the work of Steve Koonin, who says the globe is warming, but when you look closely at the science, I don't think the science says what you think it says. And from Bjorn Lomborg, who's been writing about this in the Wall Street Journal and his book on a subject, the science shows that fears of climate apocalypse are unfounded. More succinctly, we have from Greta Thunberg, after COP26 in Glasgow is over, the tweet, the COP26 is over, here's a brief summary, blah, blah, blah. And then back to Nordhaus again. My experiences tells us that we need to cool down the rhetoric so that we can understand the underlying issues. And I'm going to try to give my perspective on this subject today. I asked the question, could Nordhaus be right? If Nordhaus is right, what does it mean? And what is the DICE model, which has been the focal point of so much tell us? We have delayed and delayed, and the climate problem is growing. Governments are making aspirational promises that they should not and won't keep. We're doing the wrong things and increasing the cost of mitigation. The gaps between rhetoric and the reality threaten the policy backlash that strikes at the heart of the assumed universal participation, and this will make everything harder. Carbon pricing that incorporates the social cost of carbon is necessary, as is the other large market failure dealing with the traditional research and development and demonstration. And of course, adaptation is unavoidable, and research on and a policy for geoengineering are necessary just in case it's needed. The focus here is on cost-benefit analysis and the social cost of carbon. I've shown you some different estimates of the social cost of carbon here. One from the DICE optimal calculation, the other is the Climate Leadership Council in green, and then a couple of scenarios on the zero emission targets for the United States that I'll come back to later. But you can see there's a wide range of the numbers there, and this is important. The science helps identify the challenges, but it doesn't tell us what to do. There are trade-offs and the need for cost-benefit analysis. Of the guidepost is the social cost of carbon. There are all these uncertainties that I've alluded to and we're going to talk about. The central problem continues to be about discount rates, and it interacts with everything else, including the design and operation of energy markets that I spend a lot of time working on. So making choices. You might think that this is unnecessary, particularly for the audience of the IAEE, but there is this huge gap between the rhetoric in public and the policies we're adopting, and this perspective of cost-benefit analysis. Here I just extracted from one important document in all of this from the Royal Society and the National Academy of Sciences. And the first part is from the foreword, which is at the beginning of the study, the report, which everybody reads. And it's much more attuned to the, this is a major threat. It doesn't use the word existential, but we have to do a lot of things. The calls for action are getting louder. And this is the most important environmental problem in top 5 within the next 10 years and so on. And you get to the conclusion of the same document, and it's much more muted about what it actually says. And I won't read it all here. The references are in the back. You can check yourself, but I've highlighted the takeaway for me, which is there's an important debate to be had about choices among these options. And that's what I'm trying to do, is contribute to that conversation. Where do these targets and timetables come from? The maximum of 2 degrees from the Copenhagen Accord, and then later, more recently, the 1.5 degree target that people is very prominent in the discussion. I've extracted here some discussion of this question from Nordhaus's earlier work. And he said, where did this come from? And was there basically some cost-benefit analysis behind it that showed us the connection, the thresholds, or whatever that would lead to this? And he says the answer, the surprising answer, is that the scientific rationale for the 2 degree target is not really very scientific. And then he quotes some other things that came from the discussion of the Copenhagen Accords, and he summarizes, which I emphasize. So the politicians refer to the science and the scientists refer to the politics, but they skip the cost-benefit trade-off story that I hope most of the people in this audience think is important. More on cost-benefit analysis and the 1.5 degree target. I was selecting one paper that I was reading here about by Chen and co-authors about what to do in China. It's a very interesting paper and has a lot of analysis, but the lead-in says that the IPCC report on the 1.5 degree target was cited as recommending the target. In fact, if you read what the IPCC report says, that's not what they say. What they say is they were directed to look at the 1.5 degree target, and they were responding to describe the climate and impacts of that target. And then you go further into the document, and they have a discussion about cost-benefit analysis. And I won't read it all here. You can check with it later, but the takeaway is thus standard cost-benefit analyses become difficult to justify and are not used as an assessment tool in this report. So they didn't do a cost-benefit analysis. In fact, they explicitly rejected it. This is far from providing the full story to support a recommendation, or at least the way I think about considering the trade-offs. It seems silly that I have to make the case that cost-benefit analysis is important, and the related concept of the social benefit of carbon. I'm not going to go into all of that here. This audience is well familiar with this, but just to say that when I was discussing this with the IAEE, I thought this might be controversial, but I thought it wasn't controversial, which is amongst the economists, it's not controversial, and amongst everybody else, it's completely rejected. So it's not like we're engaged in a conversation. We're not engaged, but I'm going to try to address the critique of the cost-benefit analysis issues in the subsequent remarks, and to focus on the social cost benefit of carbon. So if you follow these conversations, you're familiar with this old picture from the US government interagency group. And the basic message here is that the estimates of the social cost of carbon are uncertain, and they're critically dependent on the discount rates. And we're going to talk more about that. There's nothing especially new here, but you can see the range of the estimates is quite large in terms of the stringency that we should be applying today. And that is an important part of the debate. The starting point for my conversation is the work Bill Nordhaus has done with the DICE model, which provides a framework and a focal point for much of the cost-benefit analysis. The high-level presentation here is taken from the paper he wrote in conjunction with the Nobel Award, where we have a welfare maximization problem, choosing a trajectory of consumption, integrating is an important word, the integral of consumption discounted at a consumption discount rate rho, and then the feasible set of consumption trajectories is determined by a lot of parameters. This is all explained in the quote here. The uncertainty analysis that Nordhaus has done is focused on the structural constraints in 2, but much of the debate about discount rates centers on the objective function in 1, and we're going to talk about both of those things. So uncertainty and the social cost of carbon. I find the debate on this subject mind-numbing. One of the reasons I agreed to give this talk when asked was because I was just trying to sort it out and have been trying for a long time to sort this out. So this is my attempt at a summary of the major issues. And I've emphasized here in bold the ones that I'm going to talk about, and then some of the others we just, for reasons of time, don't have time to address. So emission benefits accrue now and the costs are in the future. Small changes, seemingly small changes in discount rates have a major effect because of that. And there are unsettled issues about discount rates for the economy. We're involving intergenerational comparisons, and uncertainty affects everything. Economic population growth, technology change, implied temperature levels, climate-induced damages, catastrophic climate effects that could be irreversible. And then we have the adaptation and geoengineering points I made earlier. And importantly, this is a global problem, so we need broad participation in order to meet the global problem. You can take the DICE model and fixed parameters here in this uncertainty, and you can get high or low estimates of the social cost of carbon. That's not the point that it's possible, but rather that when you look at these and you try to assess the probabilities to reasonable numbers and the interaction of effects, you get a somewhat different story, and that increases the value of a model in organizing a coherent policy and supporting analysis, in a particular a model like the DICE model. Back from earlier publications from Nordhaus, this is just a nice table. I won't emphasize it too much, but it summarizes lots of estimates of the social cost of carbon. The optimal control line is what I would focus on. We have the 2.5 degree maximum, which I'll say a little bit about later. There's the famous Stern review and the debate that took place between Stern and Nordhaus and many others, where you get estimates that are just dramatically different than you get from the DICE model and the DICE model calibration. And then just with arbitrary alternative discount rates applied to the marginal cost of emissions, it shows the great sensitivity to the discount rates. So you can, this is just, again, setting up understanding, since it's in the background, that this is a really important set of discussion about discount rates. So now this is a hard problem, and I'm going to acknowledge up front that I don't think it's fully resolved, but I'll give you my take on it. First, just one way to frame this, and there's a very nice paper by Goulder and Williams about the discussion of the prescriptive versus the descriptive story. And the descriptive story being trying to get the parameters of the model to match the world. And then the prescriptive story is, I suppose you could say, trying to get the world to match the parameters of the model. And this is a continuing debate, which is, I think, quite confusing. And it mixes up a lot of different concepts. So I've listed the main elements that I see here. First is the model constructs. There's the utility discount rate, the deterministic consumption discount rate, the risk-free discount rate, the risky consumption discount rate. These are all interesting parameters that are relevant for these computations, and they're internal, they're imposed on the model. They're not observed in the world. And then there's market results from 17 countries in this case, in this very interesting paper by Barrow and Jin, about across these countries, the market risk-free premium return on government bills and the market return on capital. And much of the discussion and the debate about these musses revolves around application of the consumption capital asset pricing model in finance theory. And the basic bottom line is this yields model results that are inconsistent with market outcomes. And so we see the implied risky consumption discount rate is less than the market return on capital, whereas it's supposed to be or assumed to be the same in the DICE type model or most of these other capital asset pricing models. And where the difference between the consumption and the risk-free, which is the equity premium, is substantially different than the observed market rates for the market and government bills. And this is the unsettled equity premium puzzle. There are many papers that have been trying to deal with this problem over the years. It's an extensive literature, but my bottom line is that we've made a lot of progress, but it still remains unsettled and problematic, something that we're going to have to deal with. And we don't have the convenient resolution of this through simple empirical estimation. So we come back to the question of discount rates and the Nordhaus model. And now we're representing a deterministic model. We don't have expectations. We have this population adjustment. So it's per capita consumption discounted and then weighted by population. There's the utility discount rate. And then there's a single parameter, which is interpreted as the generational inequality aversion. This number is important in terms of the trade-off because we have economic growth occurring and the future level, like at 2100, is much larger than the current consumption level in the model. And with an alpha of 0.5, we can calculate that this implies a certain ratio of marginal changes in consumption in the future versus marginal changes today. And it's quite a big ratio. The DICE model is based on expected values or no uncertainty or deterministic, depending on how you want to say it. And hence you could derive the Ramsey rule, which is familiar to us all, which is that the discount rate is equal to the utility discount rate plus the inequality aversion times the growth rate of consumption. The model parameters are described as chosen to make the discount rate more consistent with what we see in observed behavior. And there's an issue about whether or not that's actually correct, is what's actually happening. You can actually see the discount rate that comes out of the DICE model in the picture in their base case. Arguably, the discount rates for the globe are too low relative to the empirical observations of the market rate of return. And this is something you have to keep coming back to because this is a global problem, not just a problem for the United States, and it's not just the discount rates here, but there we're trying to proxy for them with the whole globe. So it's the global proxy that's relevant. There's an alternative way to approach this problem that has received some attention, or actually quite a bit of attention in the literature, particularly in the finance literature. This is the recursive Epstein-Zinn utility function. I don't have time to explain all of this, but it is a more flexible model and introduces an additional parameter. The core element of the objective function is per capita utility, which is a constant elasticity of substitution formulation with certainty equivalent utility for the future, and that separates risk aversion and the intertemporal substitution, the elasticity of intertemporal substitution. And all these parameters are very important. This model has been is less transparent than the DICE utility function, and it has properties which are more difficult to probe and understand. However, it's certainly been used, and there are important applications in the climate policy literature that are based on using the Epstein-Zinn model. And I won't read you all of the components and the characterizations, but let me say is that the applications producing answers different than the DICE model are all determined by the choice that is made for the elasticity of intertemporal substitution, which is a hard concept and number to pin down, as we shall see, and making it different than the inverse of the risk adjustment parameter is extremely important. And there are lengthy discussions and debates. But basically, when you make these parameters consistent as they are in the DICE model, then results turn out to be the same as the DICE model. In fact, the Epstein-Zinn collapses to the DICE model and under any of these circumstances. And the Epstein-Zinn function provides flexibility, but it also comes at a cost for these climate integrated models. And the critical feature here that I'm focusing on is the premium for early resolution of uncertainty, when theta is greater than alpha, as it is in all of these applications that people are fitting to the data or assuming or calibrating. And the early resolution of uncertainty to me was a little bit hard to sort out. It's widely recognized. This is not news. It's in the finance literature. What seems to be not widely recognized is the implications, and in particular, the implications for the problem that we're worried about here in climate change. So the picture on the right that tells you the story, sort of. Here I have a very simple probability tree. And if you trace out the paths on the probability tree, you see they're the same. And the full paths have the same probability. The only difference there, and there are no decisions here. This is not, we learn something and then we change our minds. This is not an act and learn framework. So all decisions are made ex ante. And now we just have to live with, and this is the probability tree that we see. And if we're using expected utility, additive expected utility of the DICE function, the two representations of the probability tree don't matter. So you get the same answer, which is my intuition, and I think would take a lot of to convince me otherwise for a model like this. However, when you use the Epstein-Zinn utility and theta is greater than alpha, early resolution is better than late resolution. It's complicated. It's hard to solve. You have to do it numerically in a real system, but the basic point is simple. Here I've just said if alpha is very small and the time discount rate is very small, so you can ignore them, then it reduces to just the certainty equivalent of the lotteries, and the lottery on the left is 110 versus 40, and the story on the right is 10 plus a certainty equivalent of 130, and the lottery on the left has a certainty equivalent that's greater than the lottery on the right, and so early resolution is better. So I find this counterintuitive. However, I also find it, I don't know how much it matters, but Epstein and colleagues, and it's the same Epstein, wrote a very important paper about this, and I've extracted a quote, and basically what it says is that the early resolution premiums are very large in the applications of the models using the parameters that have been adopted for use in the climate models, I should say, so that you get timing premium that arise at levels that seem implausible. And I would say that's an understatement. So I find this very problematic, and it's what I don't think we should be, there's a problem here. We shouldn't be using this because it hides what's going on. You don't understand. And if you get rid of that theta is greater than alpha, then you get back to the DICE model. And it's not completely obvious to me that that's not logical. And I quote finally here that from Gollier and Hammett, under the Rawlsian veil of ignorance, the level of inequality version should be equal to the degree of relative risk aversion of the representative consumer, thereby transforming an ethical parameter into a descriptive one, which connects back to our debate. So after wrestling this for a long time, think we can't, I'm going to drop the discussion of the Epstein-Zinn story. Now we're back to the DICE model. Let's take the per capita consumption and assume that it's possibly stochastic. So we have expectations of welfare. If it was deterministic, we would be back to the deterministic discount rate I showed before. If we have a certain model of a very popular model of uncertainty for economic growth, which is a independent growth rates, normally distributed, and then a benefit function that's correlated with consumption and it has a beta in a particular form. This is a model you see all over the place in the finance literature. Then the risk-free rate is different than before, and now it's based on the mean of the growth rate, but also the variability of the growth rate. So the stochastic model, at least in principle, is important. And then when you get to the risk-adjusted rate for various kinds of benefits, and here benefit BT, the risk premium is a function of the variability, and the adjusted risk discount rate becomes the risk-free rate plus this premium times beta. And this is, of course, conceptually different than what's being done in most of the other models. And I note that this is a prescriptive conclusion as well, unless the prescription is we shouldn't worry about risk. And I don't think that's the thrust of the critiques of the climate policy here. So I think this is missing in the prescriptive model and Stern and Stiglitz and company, which we'll talk about a little bit later. And it's also relevant for thinking about the case of connecting to observed market rates. One of the key elements here is the climate beta. And Gollier has addressed this problem. As long as, of course, there's a related issue that's in this paper by a series of papers by Weitzman, but summarized in the paper by Gollier and Weitzman, where you have multiple discount rates and they're uncertain, and then the corresponding discount factor is going to be declining as a result of that uncertainty in Jensen's inequality. That's all true. That's all interesting, important. It'll come out in the Monte Carlo analysis discussed later. That's not what I'm talking about here. So here we're talking about this climate beta. And in the paper by Dietz and all, they take two different reference forecasts and then postulate distributions for all of the components of the uncertainty parameters that they, with 10 different uncertainties, and simulate according to the DICE model, I believe assuming a constant savings rate, but other than that, taking the same reference profile. And I'm not sure about the constant savings rate, but anyhow, they're simulating using the DICE trajectories. And they calculate the implied climate beta. And for the baseline, it's close to 1 for the beginning period, quite a long time, and then it gradually trails off. For the more stringent cases where you're trying to be tougher and limit the temperature, the climate band essentially stays at 1 all the way along. This is an important question and something that I think we have to be careful in understanding and including in our models. And the importance is explained in a series of papers referenced here. The cost of ignoring beta and the risky discount rate is substantial. And then it goes through examples in the DICE model and illustrating different parameters and trying different risk-free rates and all kinds of work that's going on. And then discusses the mistakes that everyone has been made, here the Gollier paper in particular. And I just capture for your summary, over the last 10 years, the remarkable stalemate prevailing in the Stern-Nordhaus debate on the social cost of carbon is another vivid illustration of our collective inability to transform our consensual asset pricing theory into practical evaluation rules. And I agree with that, and I think the impact is can be quite important. So what do we do here? Well, the target problem is a stochastic dynamic optimization problem. And although people do build these models and simulate them, and they do it analytically and by simplifying the model, or analytically by creating gigantic systems that require supercomputers to be solved. This is difficult to use these models, and particularly to get insights from them. The experience that I've had in looking at them is that they all hinge on this Epstein-Zinn utility issue. The DICE model is deterministic, it's more transparent, and utilizes an additive utility function. And then with a beta equal to 1, the adjusted discount rate for consumption and for climate change should be the same. So an objective DICE model is to try to replicate this situation. And we have this effort to get the deterministic discount rate, which in the DICE model is equal to rho plus alpha G, approximately equal to the consumption rate, which in theory ought to be close to the risk-free rate plus the equity premium, or the risk premium, which maybe should be the same as the market return. And this is true for both prescriptive and, except for the last step, which is in the beginning, but the connection to the market return is more a descriptive story than a prescriptive. And the Stern side of that argument is essentially ignoring the risks associated with consumption and the climate beta, and it basically rejects the irrelevance of the equity premium puzzle by saying, well, we should be doing something different than what's going on in the world, and the implied discount rates are low, but that creates a range of other problems that you can read about, but I'm not going to go through here. Continuing that, though, the stochastic optimization requires an endogenous characterization of the economic uncertainty. In addition, the empirical data for rates of return could be influenced by a long list of frictions, such as taxes and various market imperfections. And there's discussion on that, but I don't see that as being fully resolved either. DICE is related to the Ramsey optimization models, and it's deterministic and frictionless. So I'm letting these two symbols, omega to tau, serve as proxies for the missing effects of uncertainty and transaction frictions, respectively. And if we let rho hat be the true utility discount rate, then we could characterize the descriptive model approximation as seeking discount rates such that the deterministic rate is equal to the true utility discount rate plus alpha G plus a whole bunch of effects that are related to uncertain growth and the model of growth and those risks. And that should be approximately equal to the unobservable return on consumption, which should be strictly less than the return on consumption, discount rate for consumption, plus these unmodeled friction effects, which would make up the difference between that model and the reserve markets. And basically what I see then is that the descriptive approach of model can be seen as taking two reference parameters, rho and alpha, to approximate the risk-adjusted consumption discount rate. And the easy one to fix is the utility discount rate. So that could be interpreted just being rho hat plus these missing effects, which allows for plausible values in the discount rate. And this is basically what Pindyke did, which I referred to earlier as well. And it's important if you're going to use different discount rates to recognize these stochastic risk effects that should be included. And this is not the same thing as saying is that the deterministic discount rate is the same as the risk-free rate, or does it say that economic risk does not matter? So that is my summary of the interpretation of what's going on in DICE. There's some related work that you might find useful, which is trying to do empirical estimations of these parameters in a clever modeling approach in a paper by Newell et al. And they're trying to account for the difference between what we observe in these Ramsey models. They don't address the full uncertainty problem, But they're working on that. It's quite interesting. And what I just summarized here is their best or preferred case estimates, which give the utility discount rate at 0.8% and an alpha, the inequality version of 1.53, which is not exactly the same, but it's not that much different from the assumptions applied in the Nordhaus model, and can be interpreted as trying to get closer to the risk-adjusted discount rate for consumption. So that brings us back to the DICE formulation and the social cost of carbon. Marginal damages are rising. The discount rate is declining primarily on average because of the decline in the growth rates. The implied social cost of carbon under the optimal calculation, according to the DICE model, is the red line. The green line is this policy recommendation from the Climate Leadership Council, which is more simplified. It just assumes a growth rate that should be used and starts at essentially the same point. Now, what about uncertainty in determining the social cost of carbon? Well, there's a lot of uncertainties, and Nordhaus has done a lot of analysis of these uncertainties, doing Monte Carlo studies, when changing their parameters, and then seeing how the simulations go. The best case, it increases, his conclusion was, it increases the estimate of the initial social cost of carbon, but not by that much. The ranges of uncertainty, of course, are extremely large, and the uncertainties will tend to have some increase in the social cost of carbon, but it doesn't dominate the story. He's also looked at the related problem that the Monte Carlo studies don't address the act then learn notion, where you learn something, and that was, for example, in the Ackerman paper that I cited earlier, is an example of that, and how that affects the long-run cost of carbon and impacting the current optimal price. And he concludes in his in Nordhaus' studies that it makes a little tiny difference, but it isn't very important. And the average, or the best guess estimate of the DICE model, is pretty robust. There's a related issue, which is the equilibrium climate sensitivity, which is a topic of continuing concern. There's a famous paper by Rowe and Baker, in which they laid out a simple model on the left, in which they have an initial temperature change, which is affected by feedback effects. There's a nonlinear relationship between the feedback effects and the final temperature change. You have a normal distribution of uncertainty for the feedback effects that translates immediately into an asymmetric distribution for the final temperature change. And the asymmetric distribution has a fat tail in the long run. And so those are its basic properties. It's been calibrated and used by many others. And I just point out here that it is widely used and recognized as a pretty good description of the long run story. What has not been recognized is the transition to the story. These climate models have what they call a TCR, a transient climate response. So you have an impulse of emissions, and then after some period of time, I think it's 70 years, you look at what the distribution of the effect on climate change is, and that changes over time. That's embedded in all of these models. The climate models, it's also embedded in the integrated assessment models. What is not integrated in the not included in the integrated assessment models is the correlation between the uncertainty and these trajectories. And here I quote from the paper by Rowe and Bauman, and I emphasize this is the same Rowe as the Rowe-Baker paper. Basically said everybody's missed the point here. When you have to incorporate these uncertainties, and the logical argument is pretty simple, which is we know how much the climate has changed so far, temperature-wise, and we know how much forcing there's been. So if the long run is very large, then it must be very slow. And if the long run is very low, then it must be very fast. And when you incorporate that insight, as they argue, This makes a major risk of distorting the results in economic analysis. And my own calculations with Gert Wagner, we actually came to the same conclusion that the timing of the correlation can substantially affect the impact on the high damages on the social cost of carbon. There's a related subject which is also interesting, which is that the IAMs, the integrated assessment models, aren't keeping up with the climate models. So we have the new, more modern version of the climate models. Dietz and his colleagues compared 256 of these recent climate models to look at a pulse of carbon and then the effect on temperature. And that's the green band with the red line being the best fit. And then the other graphics are all for the integrated assessment models of what that pulse looks like and how the trajectory, and they're obviously different. So they then recommend modifying the integrated assessment models, and they did this for the DICE model. And they took what they considered to be the best representation of climate to reproduce the red line. This is what they refer to as the Fair-Joffre climate story. And then they simulated the models, and they came away with the conclusion that the initial price of carbon is $30 per ton of carbon in the benchmark DICE Fair-Joffre model and $37 in the standard DICE story. So it has essentially no effect or a very small effect, that it goes in the direction of making the cost of carbon a little bit lower. There's another part of that story which I haven't fully internalized, but it's important, and that's the second graphic on the right, which is the 2-degree cost minimizing carbon prices. And there they do find a substantial difference. And they find with the better carbon climate model, the Fair-Joffre model, the prices are substantially lower, $50 a ton as opposed to $150 a ton initially, than what you get out of the DICE model. And it is true, this is very good news. And something we should try to understand better. But it doesn't change the conclusion about the stringency of the appropriate policy now. And that's an important implication. Finally, we get to things like catastrophic effects, the Gulf Stream, and other things that can happen. The Royal Academy study, the Royal Society and the National Academy study I cited talks about these, the Gulf Stream effects and other kinds of abrupt changes. And then there's the study of the Greenland ice sheets and what's going to happen if they melt, which would be bad. And Nordhaus has looked at this again and has written a very interesting paper that's in PNAS, I've cited there, in which he looks at the underlying science, the hysteresis, asymmetries, the length at which it takes for things to happen, and so forth, and modifies the DICE model in order to incorporate all of those effects, and then calculates the impact on the initial social cost of carbon. And the net effect is to moderately, substantially moderate the impact on the present social cost of carbon. So when you incorporate it correctly, it's important eventually, but it doesn't make very much of a difference as to what we should be doing today on the mitigation front. There are many possible tipping points and that could come up, that could be analyzed in these models. Dietz and his colleagues have written a recent paper on this subject, which had looked across a range of tipping points and using the DICE model, and basically came away with the conclusion that the social cost of carbon would be increased by as much as 25% in our main specification, or they're trying to pull all of these different estimates together. This is interesting, and it sounds doesn't sound unreasonable, but it's much less than the kind of impact that we see in the debate over climate policy. By way of comparison, I go back to some of the earlier documentation from Nordhaus and his papers, and he addressed the question of things he was leaving out, like which include the sea level rise and ocean circulation and so on. And he said he didn't know exactly how to include this, so he just included an adjustment of 25% of the monetized damages to reflect these non-monetized impacts. I don't know if there's a double counting here with the using the DICE model, if it already has 25% included for these effects, but that's where we are. and what's been done here. So again, tipping points are important, catastrophic effects are important. Eventually, if they happen, but eventually and if are big qualifiers, and the implications for the current policy are relatively modest. And what should be the climate policy? So now I'm going to quote from a National Academy of Sciences study, which nobody knows about. This, I quote it because I worked on this study. So I was a member of the committee that wrote the report. Second is that after it came out, it disappeared like a stone into the ocean and hasn't been heard from since. And third is that the expectation when we started this effort is that we were going to be focusing on barriers to clean energy technologies, which were supposed to be terrific and are going to take over. If they could just get across the valley of death, as the term is used often, and we were trying to look for financing and other kinds of obstacles and market failures that could be overcome to get these terrific technologies employed in the marketplace. And basically, the conclusion that was written later is that the barriers were is that the technologies weren't really ready to compete in the marketplace. And the principal problem was we didn't have a price on carbon, which we had to do, even though, and the committee thought was extremely important, even though we were expected not to address this question, but we just couldn't avoid it because it seemed so critical. And we made recommendations, and the recommendations were focused on research, development, and demonstration. Nothing unusual here. The only thing that's problematic about this is we're not doing it, or not doing it enough. And we should be greatly expanding R&D. This is widely recognized, and from everybody from the national academies to Bill Gates. And then finally, and then the price on pollution or the price on carbon, which addresses the deployment externalities. There are some other things like learning by doing, but they turn out to be relatively small according to our calculations. So the critical issue is the price of carbon. That brings us back to the social cost of carbon and these various studies that I've identified. And here's the picture you saw before with the DICE model in red, the Climate Leadership Council, and then this study from Princeton about net zero, which sets 2050 emissions targets, and then implied marginal cost across a range of trajectories where they assume cost-effective implementation, but not necessarily cost-beneficial implementation. And the difference is whether it's above or below the social cost of carbon. And the numbers you can see are quite high, and they raise serious questions just on their face about, are we going to sustain, are we going to have to sustain, and will we sustain policies that have implied social cost of carbon, which are multiples or even close to an order of magnitude larger than those that are calculated from the cost benefit analysis that I derive from, and we all derive from DICE. There's an additional case there, which is the DICE zero consumption growth, which I included just because that keeps coming up and say, well, we may not have that kind of economic growth, and therefore the social cost of carbon is going to be more important in the future, and therefore we should be paying more now. And it's that argument is qualitatively has some support here, but it's quantitatively trivial. So it doesn't make that much difference. And it's the growing marginal damages because of the growing emissions that is driving the social cost of carbon along with the discount rates. And that's the story. Then we get into what we're actually doing rather than putting the appropriate price on pollution and subsidies and all the other things. I'll let you read this later. This comes from Nordhaus, in which he talks about his own National Academy work. And he found that none of the subsidies were efficient. Some were horribly inefficient, and others, such as the ethanol subsidy, were perverse and actually increased greenhouse gas emissions. The net effect of all the subsidies taken together is effectively zero. In the end, it's more effective to penalize carbon emissions than to subsidize everything else. Amen. And then we have this interesting interview in the Washington Post a little while back, in which Nordhaus is commenting on the shareholder revolts, such as ExxonMobil. And he says it's just another example of the efforts we're expending that are extremely costly and extremely divisive, takes away valuable time and activity. If we had a proper price of carbon, we wouldn't have to do all this. And we're going down a rabbit hole of measures. Even the central banks are getting involved. So this is the policy is just not going in the right direction. One of my favorite quotes is from Joe Bowering of Monitoring Analytics in PJM, the market in the central mid-Atlantic area, the electricity market. Subsidies are contagious. Competition in the markets could be replaced by competition to receive subsidies. It was true when he wrote it in 2017, and it's true today. A typical finding, again from Nordhaus, is that inefficient regulations or approaches will double the cost of meeting environmental objectives. Then there's a couple of studies here which essentially reinforce that point of view. I won't go through all the numbers, but you can see is that the implied social cost of carbon or the actual policies are just completely out of whack. And it's not just a US problem, it's UK and Germany examples in this other paper. I don't think this is all particularly controversial for this audience, but now we come finally to or almost finally to another picture from the Princeton study, which I found quite interesting and made a big impression on me. And here is, and it's an encouraging message. So they estimated the energy system cost under the reference case, and then under different scenarios for meeting the zero emissions target, and then compared it with historical calculations of the energy system cost as a percentage of GDP. And we might argue about the details here, but that's not important. I think it's very encouraging. So the estimated cost of the zero energy are much less than the cost have been. Policies are assumed to be efficiently implemented, of course, but if the United States chose to do so, we could afford this policy. But the same analysis raises the questions. The costs are not trivial, and would all countries in the world be willing to pay this cost, in particular developing countries where a few percentage of GDP every year is a non-trivial impact and something that they would be well concerned about. And then how much would inefficient implementation raise the cost and non-participation raise the cost to make it the targets that we're talking about unattainable? And I extracted these two graphics from Nordhaus's earlier work where he was trying to address this question. And he's using a percentage of GDP and undiscounted cost, which is, but we could, it makes the basic point here. And the picture on the left is if we have 100% global participation. And the picture on the right is if we assume that we only get half of the countries in the world, or half of the emissions to be participation. And that's a pretty depressing story if you don't get this almost universal participation. So that is something we all should be worried about. This is a global problem, and we should be setting more realistic policies that are more likely, not likely, but more likely to be adopted. So could Nordhaus be right? Yes. And then all the things I said before are true. We have delayed, and the climate problem is growing. Governments are making aspirational promises that they should not and won't keep. They're doing all the wrong things and increasing the cost of mitigation. The gaps between the rhetoric and the reality threaten a policy backlash that strikes at the heart of the assumed universal participation. Carbon pricing that incorporates the social cost of carbon is necessary if we are serious. And other elements are RD&D with less focus on deployment. And of course, adaptation is unavoidable, and we should be doing all of this research on related subjects like geoengineering just in case it's necessary. This is my presentation, which will be available online. Includes references and so on that you can look at. And I'd be happy to turn it back to Rebecca to deal with any related questions.
Sure. So you have a number of questions which are fairly long. So let me read you the full question and we'll take it from there. So this is a question from Carrie King. What about the argument that using the DICE model, and particularly its included solo growth economic growth model with exogenous total factor productivity, is inadequately to actually answer a question related to SCC? That is to say, it does not actually address feedbacks between energy and carbon technology equals TFP, for example, energy efficiency and growth. Why is DICE and any integrated assessment model based on an exogenous technology solo growth model even a feasible tool for the question of climate economics?
Well, it's a good question, and the total factor, obviously the DICE model simplifies many things, as do most of these models. The total factor of productivity deals with the economy as a whole and all of the factors, the energy efficiency story and the interaction with the cost of energy technologies is a small part of that total. There are lots of assumptions also about the level of improvement to those technologies and the backstop. So if we had a good model of how the higher cost, the social cost of carbon and the higher cost of carbon would affect the development of the tech industry, then that would be interesting. We could talk about how to conclude that, but concluding that it makes air conditioning slightly cheaper over time because of improvements in air conditioning doesn't really get to the total factor of productivity as I understand it. So it's a worthwhile research direction, and obviously, if you make assumptions that are strong enough, then you can get very high social cost of carbon. The Weitzman kind of damage estimates are an example of that, but you have to have some judgment about how reasonable those numbers are and the probabilities and the timing issues that I talked about of the temperature change. So I don't think I haven't seen, I could be wrong about this, but I haven't seen anything that I would call a convincing empirical story about how the exogenous total factor of productivity is completely wrong because it's not affecting recognizing the impact of climate pricing and climate change. Could be totally wrong because it's uncertain, but the interaction between the two is probably relatively small.
Okay, so this is a two-part question from Alex Clark. Jean-Francois Mercure and others have put together a framework they call risk opportunity analysis as a generalization of cost-benefit analysis based on welfare economics that targets the perceived weaknesses of CBA under conditions of heterogeneous agents, strong path dependence, non-marginal change, and fundamental uncertainty. Specifically, they are concerned with addressing underestimation or misestimation of tail risks and failure to account for empirically quantifiable dynamics of social/economic feedback mechanisms, or to properly account for the economic benefits of innovation. What is your view of the need for something like this and the possibility of dealing with CBA limitations in a scientific fashion? And he also provides a link to an article in Global Economic Change.
Well, I haven't read this particular paper. I think the general question is a very interesting one. And the problem with these very heterogeneous sectoral models and long-term effects and tail effects is that they're really complicated and you can't quite figure out what's driving the story. And it can matter a lot, particularly when you deal with these extreme tail kinds of arguments, tail effects. That would get my antenna to go up. And I would come back to what I said before about the Rowe-Bauman critique. Certainly I'll look it up. And but I think it's a real challenge to get something we understand and that we can use to guide policy. It would be very important to be careful about how we're characterizing all these things and how they interact with each other. As I said, I've gone through many critiques of the Nordhaus approach that I summarized in my presentation. And they all have something to say that's interesting. And then they have sometimes embedded in them things which are not completely obvious, but are actually, as the early resolution story, at least to me, sort of debilitating in terms of the critique and don't provide a helpful direction.
Okay. In addition, a comment on public outlays for deployment. Would it not be more useful to model the rate of public investment, including the use of blended public-private finance that maximizes social welfare, accounting for learning rates and so on, rather than to dismiss the challenge as too big?
Well, I think it's important, and I wouldn't dismiss it. As I said, there's a learning by doing component, for example. In that National Academy of Science and the Power of Change study I mentioned addresses this question, and it concludes that there's some premium, but when you and you should incorporate it, and you can imagine supporting it through finance and lots of other things, but it's actually pretty small. The critical problem is the social cost of carbon. If you don't account for the price of carbon, then there's a big premium effect, but that's the social cost of carbon. And after you've done that, if you have a technology which is too expensive in terms of the social cost of carbon, but is justified based on learning by doing, you have to ask a question about how big that premium is, and how much of it is internalized, and how much of it's an externality, and how much of it depends on projections of penetration in the future. And the analysis that I've seen of this, for the most part, is, well, the discussions actually of this are mostly just don't even go into this, but when you start doing that, you get numbers that are, not trivial, 10%, maybe 20% of the social cost of carbon or something like that, but it doesn't replace the basic centerpiece.
Okay, this is a question from Peter Crampton. Learning by doing would seem to be a vital factor in any cost-benefit analysis. Renewable technologies are new and experience sharp cost reductions with cumulative volume. We have seen this in wind and solar and all other technologies. Fossil technologies are old, future cost reductions will be modest. Absent international cooperation, we will be unable to manage global emissions until the green premiums turn negative. Only then will developing countries adopt green technologies out of self-interest. Thus, it would seem the role of developed countries is to develop and deploy technologies to drive green premiums negative for the most promising technologies. Does learning by doing impact the models?
Well, this is essentially the same point I made before. Learning by doing is relevant, and it is an externality, and it has all the properties that Peter Crampton summarized. But my argument is that it isn't that large. The R&D part of it is very different, and at least what we can explain of trying to get over the demonstration projects and all the other problems of having these new technologies. And everything is made simpler if we have a real social cost of carbon, which is part of Peter's suggestion as well. And I agree with that. And then the residual that we're talking about of this learning by doing is very delicate. It depends upon a lot of conditions. And for example, if the technology would never be adopted on its own, because it's just too expensive, then the learning by doing premium is, as I understand it, is zero. So what we're trying to do is to lower the cost of future adoptions, and you need a lot of future adoptions to make that beneficial to pay the additional cost initially. And so it's actually a pretty delicate analysis about getting the cost below the cost of competitive sources plus the social cost of carbon. And if we could get the social cost of carbon implemented, we'd have a much better chance of doing that. And then we would get to the point where we could stop worrying about this problem, because it would be natural and everybody would take these cheap technologies themselves. That would be the great outcome. But I don't think I don't come to the conclusion that learning by doing is unimportant. I think it is important. I just don't think it's that big. And I also think it doesn't apply to everything. It applies only to things that are right on the margin that we're trying to encourage. And that's where we should be focusing.
So I think in a related question here from Michael Grubb, he says he was curious about your brief reference to learning by doing effects being modest. In the last decade, we've seen large-scale investment in solar PV help to bring down the costs of solar from being dismissed as a ridiculously expensive way of cutting emissions to being, as the IEA called it, increasingly the cheapest electricity in history. How is that derived to be so small in the way you seem to indicate?
Well, we're interested in the prospective story, not the retrospective story. The retrospective story is astonishing and terrific. And so the decline in the cost of these technologies, such as we understand it, is amazing and wonderful and a good thing. And I hope it keeps up. And then you get to the question about how much of this is an externality and how much of it is internalized by the companies who are making these investments. That's a relevant question. If there's no externality, then there's no premium, and then it doesn't require public policy. So that's the kind of question you have to ask and answer. And then the other problem is when you get, when you go past the initial penetration, you get down into larger and larger numbers, and the cost declines become smaller, and now you have to do the kind of analysis that I talked about before. And my best attempt to understand that comes away with the externality part of this story is there's a lot of technologies which are way too expensive, and we could make them less expensive but still too expensive, but there's no learning by doing in that process in the sense of an externality that the policy should be trying to overcome. And what you need is something that's just a little bit too expensive, and then through the externality of learning by doing by a subsidy, we can get it over the threshold, and now it takes off by itself. So it's not the same thing as saying that costs come down when you build more. The answer was, well, I suppose, but what's the question is the premium. That's an externality to be the focus of public policy, and that's a different question. And there, the numbers are not trivial, but I don't think they're anywhere near the kinds of premiums and therefore require the kind of subsidies that have been suggested.
Michael Grubb has also responded that the empirical evidence on learning by doing is unambiguous, and he provides a link to the 15-author systemic review on induced innovation. So we have did you want to comment on that, or should I move on?
Well, again, I'm not arguing the principle. I'm not arguing the principle that when you build more, you learn how to make it cheaper.
Okay.
I think that's true.
So we have a technical question from Alamurad Sharifi. He says, one fundamental equation in DICE model is the need to distinguish the accurate specification of damage cost function. DICE uses the quadratic one, but recently Sigaris and Wood recommend the convex combination, which is an equation to the power of 6.7 in order to better estimate. What's your opinion?
Well, I always associate this with Weitzman's work on a much more convex, they're both convex, but a much more convex objective function. And that's an interesting question as to whether or not we think that's correct. If you take that case, which is the paper I referenced with Dietz and his colleagues, you get higher social cost of carbon numbers. Then you have to take seriously this Rowe-Bauman critique, because it matters when this is happening and the correlation with the uncertainty about the temperatures. And when you take those things into account, it dramatically reduces the implied cost of those much higher damages at much higher temperatures. So the impact on the current, it's not trivial, but it's I think round numbers like 30% increase or something like that in the implied social cost of carbon in the early days. It's much like the tipping point analyses that I summarized. So it's relevant, but it doesn't dramatically change the situation compared to what we should be doing now. It doesn't get anywhere near to the kinds of social cost of carbon that started off with the Stern critique in that debate.
Okay, so then we have just one final question, which is, do you know if anyone has looked at the impact of cryptocurrency mining on SCC through an IAM?
Say that again. I had a question popped up here, but in the chat.
Sure. Do you know if anyone has looked at the impact of cryptocurrency mining on SCC through an IAM?
Well, I think I'll take that question quite literally, and the answer is no. That doesn't mean nobody's done it, but I don't know of anybody.
Okay. Also, there's a question that's coming from John Ballantyne. What about the Mark Jacquard observations from BC experience, where he notes the politics of passing cost of carbon is extremely difficult and recommends second best approaches such as regulatory standards, CAFE standards, building codes, etc.?
Well, this is a question of political dynamics, and everybody knows that politics matters a lot here, and it's very difficult to get things done. And there are some things that are more important than others. And I don't expect we're going to get to perfection, but I am on the end of the spectrum, which says that when you reach something that is really fundamental, like the price on carbon and the ubiquitous effect through the economy, and you think about the problem that Nordhaus described of being able to subsidize all the right things so that you actually do a better job, and you have regulatory standards so that you do a better job, so that you're getting closer to what you really want. It's just so difficult that I just don't know how to do it in our economy. And we have the power of a common price that filters into the millions and millions of individual decisions that people make, and they do things in ways that are different that regulators, it would be impossible to do. I mean, it almost goes back to the communist model of central control of everything versus markets. It's almost as simple as that. And I recognize it's difficult to get a price of carbon in a politically challenging, and lots of people have spent a lot of time and have gotten frustrated and fed up and given up. We've spent a lot of time on it. We've been frustrated, but I don't think we should give up. And so I think we have to stick to this because I think it's necessary. I mean, I think it's a serious, climate is a serious problem. If we don't do this, we're not serious.
So Jean-Michel Glissant is asking if you've learned anything useful or unexpected from innovation and production of vaccines against COVID.
Well, my wife and I, at the start of the COVID outbreak, sat down and we had a long conversation about vaccines. And I said it was going to take 2 to 5 years to get a vaccine that we could address, that would address this problem. And it happened way faster than that. And it happened because we adopted an entirely different technology, not the way we were traditionally thinking about it. So I'm in the camp of Bill Gates, which is, we need a miracle. And I think I'm hoping that we're going to be surprised by some technology innovations that come out of the R&D process or creative thinking or alternative practice that are going to surprise us and are going to be terrific and are going to make this problem much easier to manage, even if it doesn't completely go away. I'm a technological aspirationist. I'm not sure optimist is the right word, but certainly an aspirationist. And I don't know what's going to happen. And that's part of the story, which is precisely because I don't know what's going to happen. It's important to get the cost of carbon into the marketplace so people have the right incentives and they're doing the right things and they're investing in the tech, trying to develop things that are going to surprise us. And I hope we get surprised, and I hope it's soon.
So you've made at least one comment on the adverse role of subsidies. The reality is that we have a huge menu of subsidies, e.g. by state, region, and technology just within the US's electric sector. This will likely only continue in a political environment that rewards the party handing out the subsidies. From your review, other than recognizing the adverse impacts, do you have any feel for how this relates to delay and harm?
Well, as I say, I think subsidies are everywhere. There's obvious political economy explanation of why that's true, with the concentrated interest versus diffuse effects. There's a whole political science literature on this. None of that is trivial. I don't pretend that it's not. It's a big problem. But this problem is so ubiquitous. We're not going to subsidize our way out of this problem, and we're have to eventually eat our spinach and do what it takes, because if we don't, we're just going to have to rely on adaptation and eventually maybe geoengineering, which I don't want to do. So I agree with Nordhaus's summary on this, and I cited some papers where people had tried to quantify these effects, but I don't think any of that's surprising to the IAEE. It's just that I don't think we should give up, and I think it's going to hurt us in the long run if we don't keep our eye focused on what the fundamental problem is, and have a price on carbon, which doesn't require us to do all the other things that we don't know how to do.
Okay, I think that's it for our questions. Do you have any closing comments, or should I go ahead and give our outro?
No, I thank you. I say I don't speak on behalf of anybody else, and I find this problem quite challenging. So, in some cases, mind-numbing, and there are a lot of loose ends here that many of which would come up into questions that I think are worth considering. But I've tried to give my take on at least a large fraction, if not all, of the debate that I found so confusing.
IAEE wishes to thank Dr. William Hogan for an outstanding webinar. This webinar will be available on IAEE's website for future download. If you're not a member of IAEE, we encourage you to join by visiting www.iaee.org. We thank you for attending, and I officially close this webinar.